I just wanted to hop on and share with you some of the ways to solve these problems. And then at the end, we'll look at a couple different possible strategies. So our first problem here for chapter 11 is using partial products. So I tried to use color to illustrate what you would do, starting with multiplying by 2 for every digit, and then multiplying by 30 for each digit, and then adding up my sum. And you can see a lot of place value understanding and is relying here to help make sure that we get the answers correct. Moving on to partial quotients. So actually the first step is over here on the left, where I'm just laying out, okay, what do I know about 3? I know 3 times 10, I know 3 times 100, I can figure out 3 times 200, 3 times 50 would be half of 300. So just getting a few of those things that I do know. Then I go over here to the right and I'm going to draw my line down, and I'm going to just take away parts that I know for sure are going to be able to be made with 3. And so I took away 200 threes, I took away 40 threes, and I took away 6 threes, and I was left with nothing at the end there. I guess I could write that in. And so there was no remainder on that problem. Moving on to the lattice model again, I tried to use color to help illustrate the steps. So the first step is in blue, where I put in my 134 by 42 on this. It's almost like an area model. The diagonals of the lattice here are really just to help us keep track of the place value. So the first block is 2 times 4 is 8. There are no 10s. That's why there's a 0 there. And 4 times 4 is 16. That's why this green 1 is here. And then I just continued that. If there was a double digit, I was able to put the tens place in the top part of that box. Then for the third step, once I've got all those green numbers filled in, I need to add diagonally down. So the first one's really easy because I'm just putting whatever's in this last box. And then for the next column, or I guess diagonal, I'm going to add 6 plus 0 plus 6. That gives me 12. So I'll put my 2 down below my lattice and my 1 up here in the next diagonal down, and carry on like that, add all of those digits. And when I'm finished, I'm left with these. I know that the 0 means nothing, so I don't need to carry it over to my answer here. So I got an answer of 5,628. Moving on to question number 4, using the standard algorithm to solve this division problem. So the first step in my division problem, I was not able to fit any 5s into the 4. So I could have written a 0 there, but I just instead looked at 41. And I can fit 5 into 41 8 times, which is where I got that. And following those same steps, when I am down at the bottom here, you'll see that I have a remainder of 1. We can deal with that several ways. We can leave it with R1. We can think about it as 827 and 1/5, or we could convert it to a decimal. And then I think the most important part is that we're going to go back to whatever the context of that problem was, especially if it was a word problem, and make sure that our remainder makes sense with the context of the problem. For example, I wouldn't have 1/5 of a person, or even a remainder of one person perhaps left out of classrooms or a field trip. Instead, I would probably deal with that remainder by adding another one. So really pay attention to the context of your remainder if you're dealing with a problem that has a story. Moving on to number 5, using the standard algorithm for multiplication. Fun fact, I have no idea when I was supposed to learn this in grade school. I don't think I learned it in grade school, and I just taught myself as an adult. So it's interesting that we're learning all these invented strategies, and I also had to learn the standard algorithm as an adult. But that's okay, we'll get it figured out. Again, I used color to illustrate the different steps. So my first step was multiplying 6 by each digit. So 6 times 2 was 12. Here's my 2, and then my 1 from my 12. The tens place of my 12 goes up above the 4. Same thing happened when I did 6 times 7. It was 42. I added my ones, and then I was able to bring this over. So using that place value. And then for the next step, for 30 times each of these digits, I'm first going to start with a 0 because 30 is a multiple of 10. I'm just going to slide everything over now using that place value understanding. So 3 times 2 is 6. 3 times 4 is 12. Here's my 2. Up there's my 1. 3 times 7 is 21. Got to remember that 1 up there, so I've got 22. And then my last step is to add those together. All right. Number 6 and number 7 on your cool down problems here, I'm going to show you 2 different strategies for each. Obviously, there are lots of invented strategies, so I'm not going to show you all of them. I'm just going to show a couple of them. The first one over here in blue is partial sums. So I would look at adding my hundreds, my tens, my ones, and then taking all of those pieces and adding them together here in the red. The second one is using a number line, and I really just wanted to put the vertical number line on this video because it is something that I really love in the classroom. I think it helps kids make sense of what they're doing to the numbers and not lose track when it starts to become a much more abstract representation here. So starting at the bottom with 356, I know I'm going up because I'm adding to it. So I know my number is going to get larger. So just setting that problem up with the black like I did helps students understand what they're going to get out of that number. When they add to it, it helps them understand where they're going and estimate where they might be at the end. So then I took apart my 175. I added 100 first, and then I thought, well, let's go ahead and add 5. 461 is where I landed, so I added 40 just to get to the next 100, and then I knew I needed 30 more to deal with the 70 in 175. The steps that I took or the jumps that I took to add here are what worked for me. So students have the flexibility to add whatever chunks make sense to them. Obviously, we want them to be efficient. Counting on by ones is not efficient. But a lot of times kids start with counting on by hundreds and then adding tens, 1 10 at a time, and then even adding ones 1 at a time. And that's okay. That's where we want them to start before they start thinking about what jumps would be more efficient. And then finally, for problem number 7 here, I used 2 different invented strategies. I'm going to start with the number line one here. And again, I set up my number line in black. I put 718 at the top this time because I know I'm going down. Because I'm subtracting, I'm going to end up with something smaller. So this way I'm going down. My number is going to be less. Again, you could totally have a number line where you're going horizontally. I just find that a lot of kids struggle with the left to right. Whereas the vertical starts to really make sense and connect to what they know about that operation. And it feels like taking away on a number line when you start at the top and go down. So anyway, I took my 398 that I'm taking away, and I noticed right away that there was an 18 hanging out in 398. In fact, it was really nicely placed. That 18 is part of 98, and the 80 would be the rest of that 98, and of course my 300. So that made this problem really friendly to solve with 3 jumps on my number line. Again, these are just the ways that I found to take my steps. Students could do a totally different set of steps as long as they add to 398 that they're taking away. That works just fine. Going over to the other invented strategy, this one was really fast to solve. This was constant difference. So that just means that I know that 718 and 398 are the same distance apart on a number line as 400 and 720. So that if both points are moving, and in fact, I have a number line over here, let's use it. If I move this number up 2, I get 720. And if I move this number, nope, 398 is not on here. There it is. If I move 398 up 2, I get 400. So if I move both points the same distance in the same direction, then my difference doesn't change. So I was able to create a much easier problem by just adding 2 to each of them, because the distance that they are apart will stay the same, which is 320. If you have not seen that strategy, that one is linked towards the top of our library of strategies. And there's a couple videos on that. It's really one of my favorites. Once kids really understand that and get to use it, they find so many ways to apply it to make things simpler. So those are our problems for this week. If you have any that are just totally rattling you and you're confused, please go back to our library of strategies and check out some of the videos there. And we'll see you next week.